And on this live stream, we are going to continue with the next session regarding additive, coating, hybrid, and incremental manufacturing. So I would like to announce as the next contribution within the paper session. And this contribution reaches us from the Karlsruhe Institute of Technology in Germany. The authors are Alexander Jacob, Simeon, Steimer, Nicole, Stricker, Benjamin Häfner, and Gisela Lanza. The paper is entitled Integrating Product Function Design, Production Technology Optimization, and Process Equipment Planning on the Example of Hybrid Additive Manufacturing. We are listening to your presentation as next.
Welcome to my presentation within the CIRPe2019 conference. Today I will talk about integrating of product function design, production technology optimization, and process equipment planning on the example of hybrid additive manufacturing. To understand the necessity of such an integration, it is important to be aware of the shortening product life cycles and the increasing innovative pressure on companies. Therefore, companies are required to shorten and accelerate their product development and production planning processes. Within each of the three domains, product function design, technology planning, and also machine and equipment selection, I will present briefly the state of the art. For product function design, it is important to know that nowadays a product design is usually iteratively validated. It means that, for example, a computer-aided design is created and then a finite element method or a computational fluid dynamic method is used to validate its functional fulfillment. Based on this degree of fulfillment, usually another adaptation of the product design is manually conducted. Automating this flow between product design and product function validation is only rarely seen. For example, topology optimization nowadays is automated and thereby optimizes product function, for example, lightweight design, automatically. In technology planning, the goal is allocating a manufacturing technology for producing a certain product or a certain product feature. To allocate the manufacturing technology to a product feature, usually certain product requirements are taken into account and are modeled. Recent approaches in technology planning focus on stochastic modeling of uncertainty about technological capacities or abilities of manufacturing technologies, or focus on special areas such as producing critical parts in airplanes, for example. The integration of technology planning is usually seen within machine and equipment selection, so that based on technology planning decisions, there are approaches which are able to select a certain machine based on the product requirements and the manufacturing technology requirements. Nonetheless, there are no approaches who are able to automatically integrate the product function design, the technology planning, and the machine and equipment selection. Therefore, I will showcase an approach who is able to orchestrate this integration and also to digitize its application. The presented approach is shown here. First, we will discuss the question of how a product model can be designed, how the manufacturing technology model needs to be designed, and how such a product model can be used to calculate and to optimize a certain product function. Based on this information about the product function, adaptations of the product model on the left side or the manufacturing technology model are possible and can be revalidated again based on the product function optimization. Secondly, from a production standpoint of view, the optimization of the technology chain can be discussed. Therefore, also the before mentioned product model is necessary to allocate a certain manufacturing technology in form of its model to produce this product or this product subset in form of a feature. Last, also the machine and equipment selection is integrated based on the final product design and the final optimal technology chain. Regarding the technology model, it can be said that, as presented in earlier work, an object-oriented design approach is highly useful. For example, a technology can be modeled focusing on topics such the producible materials, the possible dimensions of its build volume, and also the possible tolerances which can be accomplished. Such parameters are usually deducted from a set of machines with which represent a certain technology. On the other hand, the product model can also be modeled based on an object-oriented approach. The same parameters, for example, the product dimension and the product material, are modeled here again and can be, as we will see, used to compare them to machines and also manufacturing technologies. Regarding the product function optimization, as mentioned earlier, it is necessary to implement it here. In this approach, this is conducted by designing a certain method which has certain product input parameters, for example, the CAD geometry of a product, and then returns a fulfillment value. The calculation of this function and fulfillment value can be done in a case-specific way. For example, it is possible to implement simulation results from FEM and CFD models as soon as you aggregate them. It is also possible to use statistical regression models if there is no simulation available, or, for example, if there is a high uncertainty about using a simulation to deduce a good result. And nowadays, especially for more common product functions, ML-based approaches can be applied because, based on a big data volume and a black box approach, quite precise function calculations might be possible and are possible, as we see in certain fields. Following this, the interlinkage of the product requirements, the technology, and the respective machines is presented. In this example, I will highlight it based on the surface roughness, measured in micrometers. For example, a technology has a certain array of surface roughness which it can produce. The product requirement might be a specific minimal value which needs to be fulfilled. And then certain machines also add up to the technology capability, but can be allocated or can be separated to identify which exact machine actually is able to produce or fulfill a certain product requirement. In this case, machine 1 would be the machine selected to fulfill the product requirement, surface roughness. Following this, the optimization of the technology chain is presented. This begins by having the before-mentioned product model and even more information, for example, the necessary parameters, the modularization of this product model, and the dependencies between the production order of certain product features. On the other hand, we have the production technology model. We also have the same parameters, but different values here. We also have uncertainties about their technological capacities. And also, we have dependencies in between certain manufacturing technologies and their order in which they need to be used to produce a certain product. In the second step, the generation and evaluation of the technology chains is conducted. Thereby, it is necessary to identify possible technologies per product feature or module. Then it is necessary to interlink all technologies which are used to create the whole product. By doing this, we create technology chains which cover all product modules and thus are able to produce a whole product. And in the last step within this phase, a multi-criteria assessment of technology change is conducted. After the generation and evaluation of the technology chains, the optimization of the product and the production technology model are conducted. First, stop criteria need to be defined, for example, by using the same multi-criteria which has been used for assessing independent technology chains. Then, parameter gaps within the allocation of a manufacturing technology to a certain product model can be calculated and eventually be used to recursively and iteratively adapt the product model or the production technology model. More information about this iterative optimization approach is given in my work Jacoba et al. 2018, which is listed in this paper's literature. Coming to the third step of this approach, I will showcase how to use this interlinkage between product requirements, manufacturing technology parameters, and also machines. First, we have the final technology chain and the final product design. Based on the required parameters from technologies, it is possible to deduct and to select one of the machines, as shown earlier, which fulfill the product requirements, which are from a certain technology class, and which I can now produce the required product and fulfill the product requirements. In the last step, there might be several possible machines which fulfill technological requirements and which are from the ideal technology class. For them, again, a multi-criteria evaluation, in this case via TOPSIS, is conducted. To showcase the application of this approach, in the following I will introduce from the federal-funded research project KitKat a sun gear produced by the company John Deere. The sun gear has, in terms of optimal product design, the goal of integrating lubrication channels in its upper body part as depicted in the middle of the slide. So in the beginning there needs to be a product model design which covers the necessary technological and technical parameters of the product, and also there needs to be a database of the available and also maybe upcoming manufacturing technologies which would be looked at. This is then used to create and to deduce the first iteration of optimal technology chains. For example, one possible technology chain to create the product as well as the lubrication channels within the upper part of the sun gear. Laser beam melting is suggested, thereby melting a raw material, in this case metal powder, via laser beam melting, and then milling and grinding in terms of post-processing the whole gear. In this case, we produce the whole product within one additive manufacturing process and then only have certain post-processing and milling and grinding processes. Another alternative which is assessed is a hybrid production chain. In this case, we start with a shaft profile, which is usually casted, and then turn and drill some of the technical features of this shaft profile. Subsequently, we print via laser beam melting the sun gear head, and in the sun gear head also the lubrication channels on top of the shaft. Afterwards, the gearing and the spline are milled and grinded, and finally in several other post-process steps are finished. And a third alternative might arise. This alternative would exchange the laser beam melting process with the drilling process. So in this case we have a raw work piece which is larger than the hybrid process chain, which is then turned, drilled and milled so that we have the gearing and the spline. And afterwards the lubrication channels can be drilled in the sun gear top. But to fulfill this drilling, the actual sun gear lubrication channel design needs to be adapted. This adaptation of the original design of the product needs to be evaluated. So thereby certain product model parameters within the or about the geometry of the lubrication channels are adapted. This adapted product model is then used within the product function optimization and calculation to deduce a new product function value for this lubrication function. Within the project, we looked at the expression of the lubrication in terms of milliliter per second for a turning gear. Based on this product function calculation, it becomes clear that a certain function value threshold for lubrication is not fulfilled, and thereby the new design and the new technology chain of drilling such lubrication channels cannot be used further. Which leads us then to the next step, which says that we have a final technology chain, which is in this case the most economical one, the hybrid manufacturing chain, and then leads to the machine and equipment selection. Within this approach, one small example is the selection of a certain laser beam melting machine. We looked at three different machines here, the selective laser melting 800, the metal fab 1, and the form-up 350. The form-up 350 didn't fulfill the necessary build chamber volume, and then by comparing the SLM and the metal fab 1, we deduced, only for this example, that the SLM 800 is more economical. To sum this up, we discussed within this approach the product function value calculation. We then deduced certain technology chains. The cost per piece are shown here. It can be seen that the pure additive manufacturing of such a sun gear with lubrication channels is 40% more expensive than the selected hybrid technology chain, which is the result of the technology planning step. And it can also be seen that the not possible but theoretically desirable process of drilling such lubrication channels is even 90% cheaper than the pure additive technology chain. For future work, it can be said that the integration of more elaborate simulations, regressions models, and also machine learning-based approaches for the product function value calculation needs to be validated, and that also more experiments and more adaptations needs to be conducted to be sure that such approaches are not only theoretically feasible, but also deliver a real advantage in competitive product design. And with that, I want to thank you for your attention, and I'm happy to answer your questions. Goodbye.
Thank you for sending us this video, Alexander. We are back online on live stream of the CIRPe Global Web Conference 2019. After the last presentation of the group of Karlsruhe Institute of Technology about the paper entitled Integrated Product Function Design for Production Technology Optimization and Process Equipment Planning on the example of hybrid additive manufacturing, we are going to have a discussion with the presenting author, Alexander Jacob. Alexander, can you hear me? Alexander, can you hear me?
Yes, I can hear you. Thank you for the opportunity to discuss the paper here.
Thank you for giving us a good overview about the additive manufacturing research field. My first question is going to be about your industrial applications, and with this with industry related further research projects. Could you just detail it a bit more? In which direction are they going to be in the future, as well as how was it in the past?
Okay, for sure. Basically, the whole approach we are presenting here is founded in the BMBF project called KitKat, which focuses mainly on the idea of splitting additive and also conventional technologies onto the ideal product features or modules. So currently we are trying to apply the approach we discussed here within different companies from different industrial sectors. And up until now we are quite successful, but we're still working on the topic of product function optimization. For the future, we are looking into new fields and sectors, for example, special medical products, and also other areas, for example, in regards to automotive industries. And there we have good ideas how to handle the product function calculations already. And we try to use the ongoing research which I presented here as a basis to continue.
Okay, thank you very much for your answer. Could you also say some words about your domain of the optimization and also future research approaches for the optimization?
Sure. So the optimization focuses two loops which are depicted in the paper. The upper loop is about using the product function value calculation to deduct an optimal product design, and the lower loop is about selecting the optimal technology based on the product function requirements. For the upper part, we are currently looking into fields regarding crash tests and complete car simulations, which are enhanced by machine learning and also classical deep learning approaches to be conducted very fast, so that we can have some kind of live feedback which product adaptations are valid and maybe better than earlier versions. And for the lower part, for the optimization of the technology sequence, we are currently looking into a tool which is based on the showcased object-oriented programming, which is used in 3 companies to deduct for different products which parts should be produced in IM, which should be sintered, which should be casted. So we are there benchmarking especially form-based technologies and their respective post-processing chains.
Thank you for your answer. Looking at the live chat on YouTube channel, there are some questions. I'm gonna read them loud for you, yes. Also for the audience. I would like to first thank Lee for the comment and question. And he says it's a nice presentation and thanks to you. And his question is that how can we reduce the manufacturing cost with additive manufacturing by varying process parameters?
So it's a quite special question. It depends on the additive manufacturing process. For the examples of laser beam melting, there are approaches which focus on the parameters of the laser itself. So the amount of energy and the area which you influence with this energy to improve the, for example, production time. There are other approaches which are focused more on the product design. For example, about the question how many holes do you have in your product, basically. So there are applications where you have micro holes, where you want to have some kind of micro holes because it enables you to produce faster, and they're not critical for any kind of security issues or safety issues.
I see. So thank you for your answer. I would like to ask Lee to comment on YouTube live chat again if he has further comments or questions to your answer. The next commenter also thank you for your presentation first, and then ask, don't you think the processes are sometimes highly specific to the company and the abilities of the person?
Yes, I agree totally. But nowadays, as you see in different sectors and industries, there's a structural change necessary or already ongoing. For example, mentioning electric mobility or electric-based mobility. So there need to be, from our point of perspective, some approach to be able to have a continuous digital engineering process which enables you to see above your own experience and to be able to evaluate and to assess technological capabilities or also maybe new product ideas outside of your scope of competence. This is only for early product development stages and technology analysis stages, but I think it's a quite important competitiveness increasement or increasing which might be possible.
Thanks a lot again for your answer from my side and as well as from the commenters on YouTube. So thank you for your time and hope to see you soon.
Yeah, thank you for the questions. Goodbye.
Bye.